Welcome back to the deep dive.
Let's talk about galling. This term kept coming up.
Galling, I've heard it, but break it down for us. What's actually happening?
It's a form of severe wear. Well, it's more like adhesion between sliding surfaces.
Yeah.
So when you tighten a cheap fitting with poor thread quality, the friction creates heat, and that heat causes the microscopic high points of the metal to literally fuse together.
So they cold weld themselves together.
That's exactly what it is. Cold welding. The thread seize up, and you can't unscrew it. It's effectively one solid piece of metal. You have to cut it out.
Oh, wow. So you're not just replacing a nut anymore. You're bringing in saws, cutting pipe, maybe even re-welding the connection point?
And what about the system itself? If a fitting fails, maybe corrodes or shears, you could get debris in the line, little metal shavings.
Ah, I hadn't thought of that. And that debris just flows downstream.
Right into your expensive turbines, your sensitive instruments. So now, the source says, you're looking at system fleshing and retesting. You have to clean out the whole mess, make sure the system is pure again, and then retest everything before you can even think about going back online.
And the source mentions scheduling delays in this too. It's a cascading effect of hassle. While you're fixing a leak, you're not making product.
All from that one commodity part.
Okay, so downtime hurts the wallet, rework hurts the schedule. But the third pillar, this is where the tone of the material really shifts.
Yeah, this is where we stop talking about inconvenience and start talking about danger. The third cost is safety and liability.
You're not just moving water here. These are industrial settings. We're talking about acids, steam, high-pressure hydraulics.
Exactly. The source lists the risks. Leaks, blowouts, and contamination. A leak might just be a mess on the floor, but a blowout, that's a catastrophic failure of a pressurized system.
And the source specifically highlights the human element. It's not just about losing fluid. It's about employee safety.
Just think about a hydraulic line at 3,000 psi. If a fitting cracks and that fluid sprays out, it's not like a garden hose. It acts like a water jet cutter. That fluid can inject into your skin. It can cause blindness.
That puts a very different spin on saving a few bucks. You're introducing a potential point of failure right next to a person, a worker.
It does. And then you have the legal side effects compliance violations. If there's a safety incident because you used a substandard part, you're looking at fines, investigations, maybe even shutting down for weeks for an OSHA review.
Which leads perfectly into the fourth pillar, and it's the one I think is most overlooked, the ripple effect on reputation.
This is the long-term impact. It's so much harder to put on a spreadsheet, but it's just as real. The source calls it customer confidence erosion.
We mentioned missed deadlines earlier. If it happens once, maybe your customer gets it. If it happens twice, 3 times.
They start looking for a new supplier. And the source makes a key point here. A fitting failure isn't a private problem inside your factory. It becomes a public failure the second you miss a deadline.
So you save a few dollars on a part, but you lose $1 million contract because you couldn't deliver.
That is the ultimate hidden cost.
There's a quote in this section that just nails it. The source says, "A fitting that costs a few dollars less can end up costing thousands or more once failure enters the picture."
It really does sum it all up. That upfront saving is an illusion.
Okay, so cheap fittings are a ticking time bomb. But here's the question I kept asking. If they look the same, if they're the identical twins of the hardware world, how do you actually know what's quality? I can't bring an electron microscope to the store.
That is the million-dollar question. And the source has a great section called What Makes a Quality Fitting Different? That gets into the real nitty-gritty of the metallurgy.
All right, let's get technical. What are those invisible differences?
Well, it starts with material quality and consistency.
So purity, basically.
Yes. Cheap steel often has what they call inclusions. Microscopic impurities, sulfides, oxides, that get trapped in the metal when it's made.
Like air bubbles in an ice cube.
That's a perfect analogy. And just like an ice cube is weak where the bubbles are, the steel is weak at those inclusions. They become starting points for corrosion or for cracks to form.
And the source says you can actually verify this. It talks about heat codes.
Yes, this is a huge deal.
It sounds like something out of a spy movie. Check the heat code. What is it?
It's actually very practical. A heat is just a specific batch of molten metal. The heat code is like a birth certificate for that batch. It provides traceability. A quality fitting will have a code stamped on it that you can trace right back to the mill and the specific melt it came from.
And why does that matter to me, the buyer?
Because if there's a problem, you can trace it to the source. You can see the exact chemical analysis of that specific batch. With cheap fittings, the source says you often have zero traceability. You have no idea if that metal was scrap belted down somewhere or if it's high grade or from a reputable mill.
So traceability is accountability.
It is. If they can't tell you where the metal came from, you should probably assume it came from somewhere you wouldn't want it to.